Now let's go over stacked ABR, the second automatic ABR procedures. Stacked ABR is a technique designed to improve the effectiveness of ABR as a tool for identifying acoustic neuroma. It is based on derived response techniques and is developed by Dr. Manuel Dang at House Ear Institute. By now you probably have known that I admire Dr. Manuel Dang quite a bit because he has invented several algorithms that are very useful in our field. This technique is available in Biologic Navigator commercial package. Here is the figure I draw to illustrate the concept of stacked ABR. Stacked ABR is based on derived responses that we have gone over in this class earlier. So let's do a brief review. Let's say we have acoustic clicks, and that because clicks is a broadband stimulus, it will excite all regions on the cochlea. And let's say that we have the A, B, C, D, E regions. And all these regions, all these segments on the cochlea will respond and contribute to an ABR waveform like this. And so let's say wave 5 is here. And then for the derived response paradigm, the second condition is we deliver clicks together with ipsilateral high-pass masking noise. And in this case, let's say we set a color frequency at 5000 Hz. It could be at any frequency you like, but I use 5000 Hz color frequency just as an example here for now. So the second condition, we have acoustic clicks plus ipsilateral high-pass masking noise with a color frequency at 5000 Hz and like this. So in this case, the basal portion of the cochlea is masked out by the noise, so cannot respond to the ABR. So when we get an ABR, it will only come from B, C, D, and E regions. So the B, C, D, E regions will contribute to the ABR here, and we get the second ABR waveform, and let's say wave 5 is here. And for the second recording, as you now know, because the high frequency components A segments are excluded, so the latency will be dominated by portion more toward the apical end, and the basal membrane toward the apical end is more wide, soft, and floppy, so it will result in a longer latency for the ABR waveforms. So as you can see here, wave 5 latency here is a bit longer than the first condition. So the first wave 5 is here. The second wave 5 has a longer latency because the use of the high-pass noise with a color frequency at 5K here. So then now, as you know, because we have introduced the ipsilateral high-pass masking noise with a color frequency here, the ABR wave 5 will have a prolonged latency. Now if we change the color frequency from here to here, then the color frequency now is more toward the apical end, which is low frequency component. So in other words, from the second to the third condition, we reduce the color frequency for the masking noise. We lower or we decrease the color frequency of the masking noise. In this case, the third condition, only C and D and E region can contribute to ABRs. And we do get another ABR, and say we have wave 5 here. And this time the ABR latencies are determined by cochlear regions here. And again, the area under the cochlea that determines the response is now more toward the apical end because of the change of the color frequency. So as we move toward the apical end, the baseline membrane toward the apical end is even more wider and softer and floppier. As a result, the AV latency will be even prolonged. As we continue and change the color frequency toward the apical end, then the ABR wavefile will become the ABR wavefile latency will become longer and longer. So as you see, when we do a series of ABR recordings, the wavefile latency will be prolonged as we change the color frequency for the masking noise. Specifically, when we change the color frequency from the basal end to the apical end. So from the basal end to the apical end, basal end toward apical end. That is from high frequency to low frequency. So when we decrease the color frequency of the masking noise, the ABR latency will be prolonged, like this here. The concept of stacked ABR is, we have, say, several ABR waveforms. Their wavefiles are not aligned because the latency got changed when we change the color frequency. However, for the second waveform, we can temporarily move it toward the left so that its wavefile is aligned with wavefile for the first waveform, for the first recording. Same thing, we can temporarily move the third ABR waveform to the left so that its wavefile will be aligned with the wavefile of the first ABR waveform. Same thing for the fourth ABR waveform. We can move it toward the left so that its wavefile latency, wavefile peak, is aligned with the wavefile of the first waveform. So we can temporarily move all the recording waveforms so that their wavefile peaks are all well aligned. Then we can add them all together. That's called stacked ABR. Because when we do that, then the stacked ABR will have a very big wavefile amplitude because all the wavefile peaks are aligned. And when you add them all together, that's gonna give you a very big wavefile amplitude. And for this stacked ABR waveforms, you will have a very, very big wavefile amplitude. And that stacked ABR will come from all different regions of the cochlea, not just the high frequency portion, but also the low frequency portion, because it's an addition of all different recording conditions, and that includes high frequency, the basal end, also the low frequency on the apical end. So anyway, so the stacked ABR is gonna have a very big wavefile amplitude because they are well aligned, and you will represent different regions from the cochlea because it's a sum of all different conditions. Here is a figure of natural recordings to show stacked ABR. So on the top waveform is the standard ABR, no masking noise, just clicks alone. So we identify wavefile here, and then we can have clicks plus ipsilateral masking noise with a color frequency. CF stands for color frequency. In this case, 11.3 thousand hertz. Then we get ABR wavefile here. Another condition, we have clicks plus high pass noise, but this time the color frequency is at 5.7 thousand hertz for the high pass noise, and we get another ABR waveform and wavefile is here. And another condition, the color frequency for the high pass noise is 2.8 thousand hertz. We get another wavefile is here, and then another color frequency at 1.4 thousand hertz, another color frequency at 0.7 thousand hertz. So as you can see, the wavefile latency is prolonged when we change the color frequency. So these are the ABRs recorded by using ipsilateral high pass masking noise, and we change the color frequency systematically. The stimulus are clicks alone or clicks plus the high pass noise. You have been aware that the latency has been become longer as we reduce the color frequency of the bandpass noise. The neural contributions from different frequency regions of the cochlea can be attained by using this derived band ABR method. And also, derived band ABRs represent activities from more specific frequency regions than simply moderate to high intensity tone burst evoked ABRs. So these are basically the shows a real example of stacked ABR, and the figures shown here are raw recordings yet. We haven't added them together yet, so these ABR waveforms are the raw material. On the next slide, we will move the waveform to align Wi-Fi and add them together. So this slide shows the next step. We are gonna move the ABR waveforms to align the Wi-Fi peaks. So we have all these ABR waveforms, and we move them. We move the waveforms so that the Wi-Fi peaks are all aligned. We add them all together. We get a very big, nice ABR waveform here. And the Wi-Fi amplitude is from 5 to 5 prime. See how big the amplitude is, from 5 to 5 prime. It's a huge ABR waveform, ABR amplitude. So the stacked ABR is created by temporarily aligning Wi-Fi for all the derived band ABRs, and then add all the response waveforms together. Aligning the derived band ABRs eliminates phase cancellation of lower frequency activity. Thus, the stacked ABR amplitude reflects activity from all frequency regions of the cochlea, not just the high frequency regions. So this is beneficial because we not only have a big amplitude of Wi-Fi, it also represents all the high frequency, mid frequency, and low frequency components, not just the high frequencies. So as a result, reduction of any neural activity due to a tumor, say a crystalline neuroma, even a small tumor, will result in a reduction of the stacked ABR amplitude. So in other words, when there's a tumor, even just a small tumor, as long as it affects some ABR activities, it will reduce the stacked ABR amplitude quite apparently, because now we have a very big amplitude. So even just a small reduction in amplitude can be observed. And also it represents from low and high frequency activities. So as long as there is any reduction in neural activity, then the stacked ABR amplitude will be decreased. So if I put it in layman's terms, is now we have a very big amplitude. So it's gonna be more sensitive and easier to identify when there is a reduction in amplitude, because it's so big now. When we have any pathology such as tumor, that will cause amplitude decrement, and that will be easily identifiable because now we have a big amplitude response.